Welcome, everyone. I'm Penny Lewis, Executive Director of the Ecological Landscape Alliance, and I'll be the moderator for today's webinar, Green Up for Cleanup, Planting to Remediate Contaminated Landscapes. This presentation is part of the Focus on Sustainability webinar series, a series developed by a group of regional organizations known for their quality ecological education. By collaborating on these webinars, we expand the reach of our regional programs to a nationwide audience. In case you're not familiar with our organizations, they're all nonprofit and largely volunteer groups in the United States. The regional groups are the Ecological Landscape Alliance, the Chesapeake Conservation Landscaping Council, and EcoLandscape California. And now I would like to introduce our presenter, Kate Kennen. Kate is the founder and president of Offshoots Incorporated, a Boston landscape architecture practice focused on productive planting techniques and phytotechnology consulting. Kate recently authored Phyto, Principles of Site Remediation and Landscape Design. In addition to her design and consultation work, Kate teaches a Harvard Research Seminar and lectures extensively. Welcome, Kate.
Thanks, Penny. All right, we'll just jump into this. So as Penny mentioned, the title of the talk, Green Up for Cleanup, we're really going to focus on sort of the principles of phytoremediation and a Phyto 101 of how you can start to consider plants for remediating contaminated sites. So a little bit about my background first and how I got into this. As Penny mentioned, I'm a landscape architect, but I grew up on a nursery garden center in central Massachusetts, Paxton, Massachusetts, called Pleasant View Nursery. So plants have basically always been in my blood. And when I first started Offshoots, our practice, our landscape architecture practice here in Boston, we have between 8 and 10 employees at any time. When we first started our practice, our first project was actually at an old gas station site. And the town of Barnstable down on Cape Cod wanted to turn this into a new park. And they were just going to take down the gas station site and do typical remediation. And I was curious. I had heard about this practice of phytoremediation. This is back in 2005. And I was wondering, wow, is there any plants that could actually clean up the site? So I remembered hearing about these plants that eat things, right? I had gone to the Harvard GSD for my degree in landscape architecture, and I heard this guy, Neil Kirkwood, who was the chair of the landscape architecture department, talk about these plants for phytoremediation. And so I went to Neil and I asked him, you know, what could plants do for this potential site that I have down on the Cape? And he said, actually, Kate, the research is mixed. I'm not really sure. I think what we should do is run a research seminar where we can start to think about how landscape architects could use phytoremediation in the design field. And let's really dive into the academic research that's out there and start to really understand what these plants could potentially do. So I worked with a couple graduate students first, and then we started running these research seminars at Harvard to really gather new information about phytotechnologies and how it can apply in the design field. So we ran these research seminars over a series of 3 years, and that culminated in this book that Penny mentioned. So this was published 2 years ago, and with Neil as my co-author, and this is a deep dive into the science of phytoremediation. So everything that I'm going to talk about today, I'm going to give you the basic 101 overview, but there's a lot more detailed information in this book that sort of can serve as a reference. So I'm going to use the table of contents of the book to sort of set up the talk today. Is the first section, I'm really just going to talk about the fundamentals of phytoremediation and phytotechnology, how it sort of works, and what are the contaminant classifications and how we think about plants. And then the second part is I'm going to think about this idea about phytotypologies, meaning what are different phytoremediation planting types that we can consider, and show you some case studies where it's been utilized. So the first thing I want to clarify is the difference between this term phytoremediation and phytotechnology. So I get all the time people use these two terms interchangeably, but actually they're quite different. Phytoremediation is this idea that, say you have a gas station and it's contaminated and you have a spill, and then you would plant it with something to remediate that contaminant. So it might be a monoculture of grasses, it might be a monoculture of poplars, which have been used a lot in the past, but basically you're remediating a contaminant that's already been there. Phytotechnology is this term that's more encompassing. It encompasses planting uses to even prevent contamination, like stormwater filters, bioswales, green roofs, sort of anything where planting is used for a productive purpose like that for contamination. And so that's a more broad term. So we use this term phytotechnology a little bit more. It's a more recent term that you see as a more searchable term when you think about using plants for cleaning up contaminated sites. And what I get excited about this term phytotechnology is how could we set up, planting types that might go from one use to a future use and utilize design as a way to set up systems for how the site might evolve over time. So why is these concepts of phytotechnology important, right? One thing is, of course, we have a lot of Superfund sites. So this is actually a figure from a few years ago, but as of a few years ago, there were, around 1,300 Superfund sites in the U.S. And this is the EPA's list of what we call national priority sites, right? Brownfields that are the worst of the worst, the really nasty stuff. And, we have about 14 of those in Massachusetts, 112 in Jersey, to give you an idea. But, in the whole history of the Brownfield of the Superfund program, in the 35-year history, only about 25% of those sites have been cleaned up. So one use of phytoremediation is, what could we do while those sites sit vacant? What could we be testing? What could we potentially clean up? Because phytoremediation takes time. It's not a quick process. But the other thing in addition is, in addition to the worst of the worst, we've got at least 450 to 600,000 brownfields. This is the EPA's number of how many other brownfield sites there are just in the US alone. And imagine China and India and many other places with industrial legacies that we have lots of brownfield cleanup work to do. But we really think this is a very low number because this is only discovered brownfields, not the ones where tanks and other things, potentially exist. So what I get excited about is thinking about phytoremediation as a potential cost-effective holding strategy. And I say that because many phytoremediation systems can take 10, 20, 50, or 60 years to even clean up a contaminated site. But while these sites sit vacant, what could we be doing with productive plant materials while we wait for a more productive use in the future? So one of the reasons we want to consider using phytoremediation is the cost, right? When it works, which it does not work for every contaminant, it's very site and contaminant specific. But when it does work, it can be 1/10 of the cost. So typical, excavation or fill or dig and haul, as we call it, can be $50,000 to $100,000 per acre, and that's actually a figure from 10 years ago. So this is actually probably a little bit outdated, but phytoremediation can be 10% of the cost of that when it works. But so why is it only 0.5% of the remediation market out there? And the challenge is a couple things. The first thing is that phytoremediation, the term was sort of named back in the 1980s. And there was a sort of exponential growth and hype where a lot of field results or field tests were planted and the science wasn't substantiated. So what happened in sort of the early and mid 90s is that there was this major crash in the field that a whole bunch of the sites that were tested actually didn't work. A lot of these were for metals and for lead, not necessarily petroleum and the organics, but metals, lead, and those sort of things, and they didn't work. And so phytoremediation got sort of a bad name. And then since then, there's been a lot of more science-based research that's been in a laboratory and greenhouses that it's sort of, the field is more slowly reestablishing itself. And one thing that we can look at with that is that if we look, this is just up to 2009, but if we look at how many times the term phytoremediation has been cited in academic peer-reviewed journals, you can see, back in the early and mid-90s, it wasn't that many. And then there's a huge jump in this. And there's actually a whole journal in Society now specifically around phytoremediation. So there's lots of science-based research being continued. So we actually have a much better understanding of when it can be used and when it can't. So as I mentioned before, this science is not a silver bullet. There are many, many places and contaminant groups and contaminant cocktails out on sites where phytoremediation is not a good opportunity for contaminant cleanup. However, there are good opportunities too, which I will sort of walk you through. The advantages, of course, with this, as I mentioned already before, low cost, socially desirable. You know, who wants big dig and haul machinery when you can have some green plants and you can have, you know, other ecological services that happen at the same time. And it can be good for large, low, moderately contaminated with sites with very specific contaminant mixes. But disadvantages is, of course, it's not fast, needs monitoring and maintenance. We have to have long-term sort of maintenance and monitoring that if you do dig and haul, you don't have to have. Highly contaminated Superfund sites are often phytotoxic, that we can't get anything to grow. So they, even if they might have the right contaminant mix, the contaminants might be too high. And it's very site and contaminant specific. So that's what I'm going to get into some of those details today of what some of those challenges are. So the way that I like to set this up is the easiest way to think about contaminants on sites is which group of contaminants are we in? Are they organic contaminants or inorganic contaminants? And the way we differentiate this is an organic contaminant, of course, is, you know, something that it's typically a compound, something with nitrogen, oxygen, carbon as its different sort of components of the compound. And an inorganic contaminant is not, it's something on the periodic table. It cannot be broken down into other parts. So whereas an organic contaminant is a compound that can get broken down, an inorganic contaminant cannot. So the inorganic contaminants would be something like arsenic, cadmium, zinc, that sort of thing. And maybe it could be in a form, an oxidized form, or as an ion, but it's really something that can't be broken down into smaller parts. So when we're thinking about phytoremediation, we're going to be considering two completely different mechanisms. On the organic side, we're going to think about degrading that organic contaminants down into parts that are no longer harmful, right? Metabolizing it down into nitrogen, oxygen, carbon. So these would be things like petroleum, different petroleum compounds, or things like chlorinated solvents, things that we get at dry cleaning sites, that we might be able to degrade into things that aren't harmful at all. And with inorganic contaminants, we can't break it down into something else. So we want to extract that out of a site and then move it somewhere else. So ideally, we would pull it into the plant tissue, harvest it, and take it away. So it's two completely different ways that the plant responds. So, you know, we're gonna like do a little 8th grade biology here when we think about what kind of plant functions we use to do this phytoremediation of these different contaminants. So photosynthesis, of course, we all sort of understand a plant takes energy from the sun and sends down a lot of that energy down into the root zone as sugars, right? So up to 50% of a plant's photosynthetic product can be leached into the ground as sugars. And those sugars are root exudates that come out in the rhizosphere of the plant, create this sort of rich microbiology of the rhizosphere effect around the roots of a plant that aren't in typical soil alone. So if you look at my pointer way over here in plain soil, you're going to have 100 to 1,000 times less microbes than in the root zone of a particular plant. And certain plant species exude certain what we call phytochemicals, or that will create different microbial flora that are down in the soil. So through photosynthesis, we release all these sugars, we create all of this microbiology that happens in the rhizosphere. And then the other big mechanism that happens in the plant is transpiration. So the plant is also pulling a ton of water out of the soil area up into the plant leaves, using it in photosynthesis and actually transpiring a lot into the air. So what happens is actually, you know, one of my favorite quotes that I say a lot is, plants in North America move more water than all the rivers combined in a year through transpiration. So they're actually pulling all this water out of the soil and evapotranspiring it into the air. So, you know, we have this huge mechanism of water pull. So we're going to use these two mechanisms of sort of water and the sugars and microbiology as our things in phytoremediation to help us get going. So, what are in organic contaminants, those contaminants I mentioned that are compounds that we can break down into other non-harmful metabolites. We can use sort of, these are what we call the phytoremediation mechanisms. One thing is rhizodegradation, right? The microbes in the soil and the roots break down everything right in the root zone and nothing comes into the plant. This is only for organic contaminants, because mind you, we can't degrade inorganic contaminants or things on the periodic table. So rhizodegradation. Also, phytodegradation. This is meaning that it's happening in the leaves of the plant or in the endophytes that are living in the leaves of the plant rather than in the root zone. And we can also do phytovolatilization, where we actually pull the contaminant up through the plant, through the water column, and we release it as a gas. And so it might go from a liquid form to a gaseous form, and then it can get broken down in the air once it's actually released. So inorganic contaminants are completely different. They're not going to get, volatilized. Actually, I shouldn't say that. There are a few that can get volatilized into the air, but they're not going to get broken down. So what happens here is, of course, here's the category of the different these are the contaminants we typically find on sites: nutrients, the groups metals and metalloids, salts and radionuclides. And I've sort of highlighted here the different contaminants we typically find, right? Often nitrogen and phosphorus, a lot of the heavy metals, the salts and these radionuclides, especially cesium, and the things we might have from, unfortunately, explosive events. So these are the inorganic contaminants. Now, they have very different mechanisms for how the plant would work. Typically, what we're trying to do with an inorganic contaminant is find a hyperaccumulator of that particular contaminant, so we can suck up it into the plant and then chop it down and take it away. So, for example, Indian mustard is a hyperaccumulator of arsenic and some of the other metals that it would take it up at 100 times faster than a regular normal plant. So what we're trying to do here is plant a very specific plant species that would target a hyperaccumulator of that inorganic contaminant. You would plant it, and then you would hope to extract it, and then at the end of the year, cut down that biomass and take it away and landfill it at a hazardous waste material site. But again, this is way, way cheaper than actually, digging up all that contaminated soil and getting rid of it. So that's the idea here. And if we can't get the metal actually up into the plant, the other objective would be to just stabilize it on site. So how we would typically use sort of a clay cap or another sort of topsoil cap, we can use plants in the same way to just stabilize a metal or an inorganic contaminant on site, because phyto extraction, which I'll get into more detail, can be very, very difficult to do on site. So, if you're sort of here with a potential metals contaminated site, unfortunately, there's not as many good case studies on that site except for a few metals. So I'll kind of go through those in details. We kind of call this Phyto Confusion, right? These words, phyto extraction, phytohydraulics, phytodegradation. What we try to do is to explain this to landscape designers and sort of the public is just remember that organic contaminants we show are kind of circles here, right? Circles is our graphic, and the inorganic contaminants are squares as we go through. And we sort of gave these little cheat sheets. Rhizodegradation, happens in the roots, in the leaves here, or it gets volatilized into the air here. Whereas extraction, you're more pulling into the plant or stabilizing it, you're locking it into the soil. So, we give some sort of graphic keys through this presentation and throughout our book if, you end up using that as a reference. So now I'm going to kind of go through and get into the details of which contaminants we have more opportunity for phytoremediation and potentially less when you find it on a site. So we developed this chart that basically a landscape architect or designer could use, that you go in and say, if I have this potential contaminant group, when is there a good opportunity for phytoremediation? When should I be thinking about it? Or when is there less potential? And what is the time frame? Down on the bottom is the other axis. Less time, really 5 to 10 years or 60 years or more over on the right-hand side. So when we look at that here, this is sort of the go-to chart that actually you can find this on our offshoots website as well. That is a good resource for people. Is If we look up in this upper left-hand corner, this is where we have really good potential field opportunity for removing that contaminant with a plant. So, you know, nitrogen and phosphorus, of course, because there's plant macronutrients, there's lots of opportunity there. Chlorinated solvents, so like I mentioned, PERC, which is like a nasty thing from dry cleaners. TCE, which is a typical fire retardant. There's a 7-mile long plume of TCE underneath Cape Canaveral. It goes very quickly down into water supplies. Really great case studies with TCE and PERC and removing chlorinated solvents from contaminated groundwater and soils. Petroleum, many of the petroleum compounds can be quite easily broken down with plants. Some of the PAHs, or these are the polycyclic aromatic hydrocarbons or ring structures. There's some potential for these. They can be more difficult. And some of the pesticides, we have lots of good potential. The other thing is, in terms of metals, nickel, selenium, arsenic, and some cadmium and zinc case studies have some good potential for extraction and taking those out of sites. These other ones that are over on this side of the chart here, there is not as much potential for actually pulling it into the plant or breaking it down. We could certainly cap these on sites with plants, so there may be other strategies to pull these particular contaminants out of stormwater or out of groundwater. But if we're just talking, this chart is really just about getting things out of soil. These things are going to be very difficult for any plant to actually remove, as well as the explosives. There just aren't that many good case studies for explosives as well, unless it's in groundwater or in stormwater. So like I said, this chart is really just for soils, and these contaminants up here are really the ones that we have great opportunity. So, you know, where do we find contaminants? Like I mentioned, stormwater and wastewater, which I'm not going to talk too much about today because many of us have done a lot of stormwater bioswale interventions. Air, which is a whole nother topic. I'd love to talk about that in a different lecture, but I'm not going to talk about that today. I'm going to focus more today on soil and a little bit on groundwater as well. And what are some case studies showing you where some things really have potential. So one thing we did in the book is we created what we call these phytotypologies. These are 18 different planting types to remediate different kinds of contaminant groups. So I'm going to use this, I'm just going to talk about 3 or 4 of these today. So there's many, many more to explore here, but I'm going to show you the most basic ones to sort of explain the concepts of how organic and inorganic contaminants can be removed. So the first one is this idea of a degradation cover, hedge and living fence, or a bosque. So this is the idea that it degrades the soil contaminant in either shallow, medium depth, or deep contamination up to about 20 to 30 feet. That's about the deepest that we can go. So mind you, if your contamination is deeper than 20 to 30 feet, we're not going to be touching that. And so degradation, we're really only considering organics. We're considering chlorinated solvents, pesticides, petroleums, and then also it's not really degradation, it's more phytometabolism of nutrients, but we can also kind of ramp up denitrification and take nitrogen out of soils and convert it back to a gas. So we kind of looped it into this as well. So a degradation cover would be basically an herbaceous species that we're getting down to a contamination zone of about 5 feet deep that we could do degradation of that contaminant. A living wall or hedge or fence, many of these are, willow is a very, very common species for phytoremediation, utilized for many, many organic contaminants. We can get 4 to 5 feet deep in those systems as well. And then this idea of degradation bosque, we say in here, the zone of contamination is maximum 10 feet deep for a traditional tree species that's planted with a deep root technology. If we're searching for groundwater, as I mentioned before, we can get up to 20 to 30 feet deep with phreatophytes, which I'll talk about in a little bit. So I'm going to show you a couple case studies to sort of describe how this is used. So this is out in Bancroft, Wisconsin. Sand Creek Consultants, a civil engineering and phytoremediation consulting firm out in Wisconsin, worked on this site. And what it was is that this is a pesticide. Their pesticide was Dynaseb. And the issue was is they had these, you know, big aerial spraying operations that all they did in the 50s is they went back and dumped the extra barrels and buried them out back behind the hangar, and they leached into the public drinking supply. And not only did the pesticide contaminate the soil, but it contaminated groundwater and drinking wells that were for the local town. And so when we look at where this Dynaseb plume was, is they had a very big hot spot where the original barrels were dug out. And then it had contaminated a very large area with the groundwater flow going in this direction. And so what they did is they actually planted a whole series of plants, which I'll show you over this. And they actually degraded the entire plume, and there was no detection down gradient from this within 4 years. So this was effective within 4 years. So here, the first thing they did in the project is they go in and they do what we do a pilot project or clonal testing. So they went in and in this case used various species of willow and various species of poplar because they were dealing with both soil contamination and groundwater. So one of the reasons we're going to see that poplar and willow are continually utilized is poplar hybrids tend to be a cross of these different species that are here, and they can grow up to 4 to 8 feet a year. So if you can imagine that we're trying to ramp up all of those sugars that I mentioned going down into the soil and basically creating the plant as a catalyst for the system. It's leaching sugars, it's sucking up a ton of water. Something that is putting on a lot of biomass and growing 4 to 8 feet a year is going to be very, very effective. So these plants that put on a lot of biomass, like willow and poplar, tend to be many of the species used in phytoremediation systems. The other thing about willow and poplar is they're phreatophytes. So as I mentioned before, you know, typical trees, actually, we really usually see them about 3 feet and above their root system. Some get down to 5. But phreatophyte trees can reach as much as 20 feet, and if planted deep root, can really get down, and I'll talk about what that means, but can really get down to 30-foot depth. So willows and poplars are phreatophyte trees, meaning they search for groundwater. They'll send down a big taproot that will search for groundwater. So those trees can be very, very effective when we have contaminated groundwater plumes below the surface. Typical phreatophyte trees, you can see these are some of the other plants that are out there that some of them will really go and search for that groundwater with the taproot. And you're not really meant to read the details here, but one thing I want to show you is the transpiration rate of a poplar, meaning how much water it sucks up and transpires. You know, this is the amount of gallons per day. So a 30-year-old poplar, you know, can transpire up to 200 gallons of water a day, meaning suck it up and transpire it into the air. So you can do an awful lot of removal if you have a particular contaminant that's in the groundwater. You can suck up a lot of water and get that volatilized into the air. And then, like TC, what happens is when the UV rays hit it, it actually just breaks down when it gets to the air, or it might get degraded as it passes through the leaves. So, so you can see why poplar is used often in many of these. And you can also see, you know, cottonwood, just a straight species, is often utilized, as well as many of the willows. So this is how this particular site was planted. They went in with small 18-inch cuttings. They ripped the soil. They went in, they planted them, and 2 weeks later, this is the irrigation tube, because mind you, of course, poplar needs a lot of water. So those cuttings aren't going to survive unless you provide it with an irrigation source, unless you're in a very wet climate, or you're, you know, really planting in the dormant season where you're going to have a lot of natural water. But 2 weeks, you know, 4 weeks, you can see how fast this thing is growing. By 1 year, this plant is at 6 feet tall, as well as you can see this is a willow cutting on the other side. So this is how much they suck it up. 2 years, you know, we're really up in the 12 feet tall range. And 3 years, you know, we're much higher than that. You can see in this particular case, they're monitoring the sap flow to figure out where the Dynaseb is being broken down. They actually figured that they found in these studies that it was in the sap flow. Partially, it was getting broken down in the roots of the plant, and partially in the leaves of the poplar. And the other thing on the right hand area that this shows is, you know, they have to do continual monitoring and maintenance This is a deer fence because, of course, poplar is loved by deer, and this would just get mowed down. You know, moles and voles and those sorts of things can also be a challenge, which is why you see some of these sort of installations as well. So that can be a challenge. And then at 4 years, you know, this actually creates kind of a beautiful space. And that's how I started getting excited about these things, is how can we use these contaminant removal species that very often we won't design with poplar and willow because they're very quick growing and they may not be very long lived, but maybe they could be a holding strategy or sort of nurse crop for our other planting strategies that we might do. And they can help, you know, buffer or remove potential contamination on site, or buffer future contamination that could be occurring. So I like this slide because what it shows here is these poplars in the center weren't a different clone. All it was is that the poplars on this side and the poplars on this side actually had less contamination in the soil. So the growth of these ones in the middle was really a sentinel to show that this was a cleaner area of groundwater below the surface. So there's this whole other field of phytoforensics where we actually use plants to determine, we can tell the water quality and the soil quality by their growth, and we can do testing of the plants. But again, that's a whole nother lecture, but really exciting stuff, this idea of using phytoforensics or plants to actually do monitoring of the soil and the groundwater below. So, you know, how would this concept be used, right? This site was cleaned up in 4 years. It was very inexpensive. You know, these poplar cuttings can go in for, you know, they can be purchased for a little as 80 cents a cutting. The installed lifetime cost of the tree, they estimated it at about $12 per tree. And so, you know, how can we use this in landscape design? You know, one of the things I mentioned, sort of that gas station project that I talked about, you know, how could we better design just gas stations while they're being utilized to actually, you know, what if we started to plant these buffers of tree species around the edge that might have phreatophyte qualities, that might be able to buffer some of the small spills that occur, or even things that might happen in the auto repair shop, or old contamination events. So how could we start to think about landscape a little differently to help buffer those potential contaminated sites, as well as, you know, sites that are contaminated with petroleum from the beginning? The other thing is light industry, right? Of course, you know, we don't mean for there to be spills, but there's accidental spills all the time of hydraulic fluid and other sort of degreasing agents. All of these things have been shown very, very well to be, you know, when one caveat is I have to mention, it only works when the soil profile also works. So if you can imagine you have a very clay-based soil and you can't actually pull water or get root penetration in it, you're not going to be able to remediate that contaminant. It's going to be too tightly bound to the clay particles. So, you know, it is very site specific. You can't assume it's always going to work, but that's when you sort of get a phytoremediation specialist involved and say, you know, I think I have a good opportunity here. I have petroleum. It's within 30 feet. You know, maybe we could consider phyto, and then we kind of come in and look at the qualities of the soil and start to do some borings and see if there's a possibility there. So in light industrial sites, I like to get excited about like planning. We're doing a lot of planning in our office for potential new light industrial developments and, you know, makers communities and that sort of thing. If you have a light industrial site, you know, could you think about planting a buffer of species that are down gradient, especially down groundwater gradient of a particular use, so that you might be able to capture and think about, you know, capturing any contamination events that might occur through the life of that light industrial use, in addition to just thinking about remediation. So this idea of this interception hedgerow, it's the same exact idea that I just mentioned. Is instead of planting a whole mass of, say, a tree or a plot, like, can we just plant a single row of something that at least we can remove some of the contaminants as the groundwater passes by? So maybe we don't remove everything, but just some of it. And so, for example, when might this be utilized? One of the things that we don't like to think about is sort of graveyards and cemeteries, right? Formaldehyde is the major ingredient in embalming bodies. You know, it's a EPA contamination source. When formaldehyde is in groundwater, it's toxic and carcinogenic. It can cause cancer. But when it, as soon as it hits the air, it actually breaks down very, very quickly. So what we need to do is get it out of groundwater supplies and into the air through plants so that it can get broken down. So one thing that, you know, the other thing is old graveyards and cemeteries often had arsenic as another embalming method. So one thing we can think about is how can we use phytoremediation plant species that we could actually, you know, line our streets and create buffers that are down gradient of maybe the where the embalming events might have happened, or the, you know, that folks might be interned, that we could actually clean up some of those contaminants. So kind of, you know, not fun to think about, but a good way to think. We design a lot of parks and these sort of things that are located near cemeteries. This is also just the idea of a funeral home. Like, how about you design the landscape of a funeral home? If you're going to have, you know, you can potentially have spill events that would happen where the embalming might happen. How could we think about a down gradient buffer that might clean that up and actually evapotranspire and break down those contaminants before they move into a larger groundwater supply? So it's just sort of things to think about with these particular land uses that of how you might consider those. One of the other organic contaminants or one of the other phytotypologies that we can use for both organic contaminants and the macronutrients, especially nitrogen, is this concept of phytoirrigation. So this is the planting type. That's the idea of, you might have like a contaminated water source or groundwater source, or even maybe there's a pond that's contaminated with excess nitrogen. You might put in a pump, maybe it's even solar powered, and you could pump up that contaminated water onto a plant that would then clean that contaminated water and transpire some of the excess water into the air, and then essentially cleaning up that contaminated water. So this is especially useful in contaminated landscapes like landfills. So landfills can generate a lot of leachate. This is the nasty sort of, especially unlined landfills, meaning if they weren't capped and they're old landfills that exist, you get a lot of rainwater that comes through those with leachate that can be contaminated very often with ammonia, which is a form of nitrogen. They can be contaminated with salts, often heavy metals, and it can come back in and then often gets held in a leachate holding pond that then has to be remediated somehow. And so we can think about using phytoremediation plant species to actually take that contaminated water and potentially, either if it's an unlined landfill, we could plant species right on top of that and either water it back onto here and clean up some of that water, and also prevent stormwater from coming through the thing which we call an ET cap, or evapotranspiration cap, with phytoirrigation. Or we could actually have a plot off-site, say over here, that we might irrigate the plants with the contaminated water and then do the cleanup that way. So one of the case studies that I love to show is this case study has been going since the early 90s, the Riverbend landfill. This is CH2M Hill, which is actually no longer CH2M Hill, but they were recently purchased by Jacobs. They did a landfill phytoremediation site out in Oregon in the Willamette Valley. That this is actually a lined landfill, but the water still can seep through the seams on the cap and generates an awful lot of leachate that is very, very high in ammonia. The other thing it's also high in is its temperature. It's actually very warm, and with all the cold water fisheries in Oregon, you want to make sure that the water that you're releasing back into the streams is actually cold. So what they do is they collect the leachate and they actually run it through. Again, this is poplar is used here. Poplar is sort of the workhorse of the phytoremediation field for all those reasons I mentioned before. And they basically drip irrigate this from below, and they actually cut this down every 7 years or so and chop it up and make a product that they create chips to create cardboard. So they actually get an economic product that is basically a fertilizer in a way, an ammonia-based liquid fertilizer that gets watered onto the trees. They get this byproduct, and the leachate, instead of having to send the leachate 300 miles to get processed in a hazardous materials facility, they actually clean it up right there on site. This same strategy was used by the Woodburn Wastewater Treatment Facility, which is just down the road and also in the Willamette Valley, where they basically planted 84 acres of poplars all around this wastewater treatment plant. The wastewater treatment plant, instead of doing tertiary treatment, meaning in a wastewater treatment plant, we usually treat the water primary, secondary, and tertiary. And tertiary treatment processes take up the majority of the energy in the treatment process. And instead of tertiary treatment through a traditional process, they actually water it onto this 84 acres of poplar, also harvest it and use it to make cardboard and get an economic product. So in here, you can actually see that they're irrigating through these micro sprays. This could actually be done underground, because if it was done underground, you could actually have people walk through it and use it as a recreation site, and it really wouldn't be a hazardous material site at all. So these could actually, I get really excited about the other kind of potential uses that could get layered on. So here you can sort of see that they're kind of cathedral-like. These, you know, in this case, these were 10-year-old poplars about to be harvested. This was us at the International Phytotechnology Society meeting, walking through these sites, and they're quite beautiful. And the way that, you know, we can apply this locally here in our work at Offshoots, we've been working with the Cape Cod Commission. You know, there's a major kind of nitrogen pollution problem with the groundwater on the Cape. And this is primarily because, you know, first of all, it's a sole source aquifer, meaning all of the drinking water that's supplied to the Cape comes from the rainwater that falls directly above it. It's all linked together, the aquifer underneath. And it's getting polluted because, you know, 80% of the nitrogen pollution is coming from septic systems. There's very little sewer on the Cape, so the septic systems are leaching nitrogen directly into the groundwater. And so the challenge with that nitrogen is it gets into the groundwater, and when it hits the estuary, when it hits the saltwater estuary, nitrogen is actually typically limiting and a limiting factor in saltwater ecosystems. But when you add nitrogen, of course, you get this huge bloom of algae that sucks up the oxygen and takes the light away, and then the eelgrass is gone and the fish disappear. And then all of a sudden, you know, the scallop industry starts declining on the Cape because we don't have the eelgrass and these other things, and people start to get concerned. And we have these huge algae blooms, and we don't even really know what the pharmaceuticals and pesticides and metals and other things in that wastewater is doing. You know, we joke around about, you know, how is it affecting the ecology there? But it's true, we really don't know, especially what the pharmaceuticals are doing. So we've been working with the Cape Cod Commission to develop a strategy at the site scale, the neighborhood scale, watershed, and Cape-wide scale to think about, you know, can we look at composting toilets? Can we look at vertical wetlands and phyto buffers? Can we look at phyto irrigation to water our contaminated water back up onto plots that might be able to remove the nitrogen? So things like the site scale green infrastructure, instead of your leach field, you know, could we have these ideas of composting toilets or vertical wetlands that we might remove the nitrogen? Can we think about these phyto buffers like I just mentioned? Or there's actually been a lot of work with UMass and Anna Maria Frankic in Wellfleet about using the oysters to actually remove the nitrogen from the estuary as it's there, or these wetlands, surface flow wetlands, to remove the nitrogen. And sort of to bring it back to the topic of phyto irrigation, we've been talking about how can we either pump up the contaminated water from the aquifer or do tertiary treatment when we do have sewer to remove that nitrogen. So you know, it's very interesting, I think, as a planning strategy to think about how we can integrate some of these more long-term plant-based systems into green infrastructure. And then, so I'm gonna talk a little bit more about the inorganic contaminant side. I kind of showed you all the really great opportunities on the organic contaminant side. And then I'm gonna spend the next 5 minutes or so just kind of talking about the inorganic side. So, as I mentioned, what you would typically do with an inorganic contaminant, something on the periodic table, is you plant a hyperaccumulator that then you would harvest. The challenge is back in the 90s, lots of sunflowers were used for lead. They were planted out, it worked. Sunflower is a hyperaccumulator of lead in a greenhouse. But the problem is when you plant it out on a site, there's limited what we call bioavailability of that contaminant. So what I mean is you might have a whole bunch of lead in the soil, but a lot of that might be bound to the soil so tightly that only a very limited portion is actually bioavailable for the plant to take up because of soil chemistry. So the challenge is lead. You can see down here, sunflowers do not work for lead on sites. I know it's a challenge and people get sad about that, but you can still find a lot of information on the web of people trying to do it. But it's old research that was done back in the 80s and 90s. Really, the only places we can really think about phyto extraction of plants in soil is nickel, selenium, arsenic, cadmium, and zinc to get it into the plant and then harvest it. As I mentioned, just to be clear, lead and chromium and many of these other contaminants can be taken out of stormwater, but that is really through the filtration of the roots and the contaminant being locked up in the roots of the plant and in the soil. So the soil basically acts like a big sponge. It doesn't get into the plant and the plant doesn't take it up, right? It's really just these particular contaminants that the plant actually can take up if you use a hyperaccumulator. So, you know, how have hyperaccumulators been used in the past? Alyssa Morale has been actually used to phytomine nickel, where they take the plant, they turn it into an ash, and they actually use it to mine the nickel. This is being used extensively right now in Europe. Eden Space has developed this arsenic fern that we can actually plant on arsenic contaminated sites. This is actually a site here at Offshoots that we used Indian mustard to actually plant an arsenic contaminated site that was a residential property. We did testing to take up, we went out there and actually seeded the Indian mustard in collaboration with UMass and did a study to see how much arsenic we could take out of this contaminated site. Arsenic is very scary because it's, again, carcinogenic, can cause cancer, and is in many, many residential sites, especially because it was highly used in orchards and pesticides, and also in pressure-treated lumber up until 2004. So we have lots of arsenic-contaminated sites, and unfortunately, our study ended quickly on this project because the homeowner decided to sell her house, so actually, solution of pollution is dilution. She added a whole bunch of clean soil and then it brought the background levels of arsenic down enough. We anticipated that we were going to need 4 years of crop rotation to remove the arsenic from this site. So typically instead what we do for inorganics is that we do planted stabilization mats. So this is the idea that we would plant something to hold that contaminant in place so that it's out of risk of human and animal consumption. So right, this is what we do when we cap sites. So this is typically a better strategy for inorganic contaminants. Things like, if you can imagine lead pollution that you might have, especially in the first 3 feet of a building that might have lead paint, we would want to just cap that on site. So the best thing we can do is plant very, very thickly, maybe low mow polyculture lawns that wouldn't show any soil. Because the primary thing, just to touch on lead a little bit more, is the primary thing we have to think about with lead is soil dust exposure. If kids or adults or anyone else eat soil dust, that's the primary way they're getting lead into their system. It's not because they're eating a carrot or something grown that was in, is getting it into the plant. It's actually the soil dust attached to the carrot that they would be eating. So what we want to do, that if we have lead contaminated landscapes, of course, we want to have raised bed gardening so we don't have the soil particles on the plant. And also we want to have, very mulched areas and limit soil dust exposure, especially with lots of grass plantings and heavy vegetation that keeps that soil dust in check. So that's really what we want to think about with lead contamination and other metals contamination. And like I said, really the only good opportunities for extraction: nickel, selenium, arsenic, and then some zinc and cadmium. But the other ones are really at this point, quite difficult to do. So to wrap up, and now is a great time that if folks have questions, if you can type them into the box, we'll spend the last 10 minutes I'll answer any questions that might have come up. But as I mentioned, we have these sort of 18 different planting types that I only touched on a couple of them today, of how the plant acts in the system. And I didn't even talk that much about particular plant species. For each of these planting types and each of the different contaminants, we have lists of the plant species for that particular contaminant in the book. So there are all these long Excel charts. We also have many of them for free on our website that you can access. And you can also send me specific questions about if you have a particular contaminated landscape and looking for species. But we have very specific species lists in the book. So the biggest thing that I want people to remember is that, you know, the difference between an organic contaminant and inorganic contaminant, that really we have lots of potential on the organic side, especially in groundwater and soils for degradation. Whereas in organics, it's really going to be more for these very few, the extraction, and we're going to really just stabilize it in the soil. And that, you know, I hope that I kind of encourage people here that, you know, as designers, or us in our practice anyways, as a landscape architect, we bring all of these other folks to the table, the ecologists, the soil, the civil. And now, you know, we really hope that for particular sites, when it comes in, is you have this sort of phyto specialist. And that may not necessarily be us. It could be offshoots, but it can also be, we have lots of other remediation specialists that we work with on the science side to help integrate these strategies into your landscape design and other, you know, potential planning projects. So with that, I'm going to conclude, and this is my email address, because you can also, if you don't have time for questions now or want to get in touch about something specific I said, please feel free to email. And I'm going to turn it over to Penny now, who will take and post the questions.
All right, thank you, Kate. That was certainly a lot to digest, and lots of very encouraging information. We just have a couple of questions. The first one is, you talked about a lot of different ways that you could use plants as remediation, but this question is more about, in a site where you just have typical urban soil, are there plants that could be added to a general planting design to achieve phyto-type benefits with various climate contaminants?
Yeah, absolutely. So in urban fill soils, you know, it really depends sort of where you are, but very often we have coal ash, right? Coal ash is is basically a type of petroleum that can be broken down more with certain plant species that have these very rhizomatic, thick roots that can get down. You know, you would really want to get the roots as deep as possible. So, you know, if you, for an example for that would be, again, the best way to figure this out would be to either go to our book or another resource and look up coal ash and look at the different plant species that have been utilized in trial studies. But they tend to be the prairie grasses, that like things like switchgrass, little blue stem, rhizomatic grasses that will get a very deep root growth and have a lot of little nodules to have plants start to have microbes on them to help break down that contaminant. The other thing in that is that legumes, adding legumes to your mix, there's been many phytoremediation studies that have shown having a legume added to the general mix really helps both with, if you had extra, obviously extra, you know, nitrogen in the soil, it's going to, you know, make organic nitrogen in the soil. It's going to make the other plants grow better, but it also helps speed up the microbiology of other plant microbes that are in the area. So adding a legume to the mix can be very, very useful. The other thing with urban soils is often, if you've got groundwater moving through it, if your groundwater is high, if you planted, say, a phyto buffer for organic contaminants on the low side or on the down gradient groundwater side of that urban soil, you could potentially, if the contaminants were getting leached out of that urban soil, you could capture and try to treat those before it went on to the next site. So those are all some ideas. And if you're really specifically interested in that topic, one of the phytotypologies or the land use types that we look at is the vacant lot in our book. And you can take a look at the idea of the vacant lot. And we talk quite a bit about urban soils in there and strategies for that.
Excellent. Thank you. The next question is, you talked a lot about the great benefits of using poplars, and the question is there a next best plant option since poplars are so short-lived in a regular design setting?
Yeah, so again, that's where I see phytoremediation evolving is that a lot of the early research was done on poplar, especially because it was so effective and works really quickly. There's a lot of newer research going on for plants that may not grow as fast and might have a longer time horizon, but the plant would have a longer time horizon, but the cleanup would also have a longer time horizon. So there are other species for sure that have been tested. They tend to be the plants that have a high transpiration rate and again, a deep root structure. So again, that probably the best place to refer you is again to the book. You can look up the particular contaminant you're talking about, but there's a lot of work with many different varieties of sycamore, including London plane tree. A lot of the alders and birches have really great properties. Again, those are on the shorter lived pioneer species side. But they, if you're trying to ramp up the system usually you're looking for a lot of biomass growth, so the plant expires soon. So we think think about planting other hardwoods and other things as part of the design so that you might integrate some of those faster growing species. And it doesn't just have to be poplar. There are other species as well, especially for different climatic regions.
All right. The next question is, do you have a recommendation for any species that could remediate road salts?
Yeah, so there is, and I didn't even touch on that topic. There's this whole area of species called halophytes, right? And what halophytes are is they're plants that will live in salty soils that will actually take up the salt and excrete it onto their leaves. So this is the million-dollar question. Most road salt actually kills plants. And when chlorine, when road salts get into water, the chlorine splits off and chlorine moves right through all wetland systems. It still keeps polluting things. So it can be a challenge. So there was a lot of work in this area of looking at potential halophyte species to be able to plant and extract the salt. I have not seen, there's a lot of lab work. I have not seen field studies that have been able to mitigate and remove salt. So at this time, the strategy for dealing with road salt is plant salt-tolerant plants that will live. And the only other thing would be is if your salt is traveling by water, stop that water by creating a buffer of plants. Like, again, there's many actually poplar species that have been bred to tolerate salt. Same thing with willows. And they can take a lot of the water and transpire it, and then it prevents the salt from moving and it will sort of hold it on site.
Okay. And we're fast running out of time here. The last question is, can you repeat the name of your book and when was it published?
Yeah, sure. So the name of the book, I'm just going to scroll back here really quick just so you can see the cover, is, and I'm sorry, this is not, I don't mean for this to be a marketing, I always joke around, this is not meant to be a marketing solicitation because I literally make $1.50 on every copy of this book. It's not about that. It's just about getting the information out there, and we spend a lot of time kind of organizing the information. But it's called Phyto Principles and Resources for Site Remediation and Landscape Design. It was published in 2015, so it has very current research because it's only 2 years old, and you can find it on Amazon, or there's a link to it on our website. It's available through Amazon or the publisher.
All right, excellent. Well, thank you so much, Kate, for all of this really in-depth information. I appreciate you sharing your time. Thank you again, Kate, and good day to you all.
Great, thanks, Penny.